Hey everyone, Brendan here. So today we're going to be taking a look at the Carnot Engine. The Carnot Engine, which is essentially a term describing more broadly a thermodynamic cyclical process, is an essential topic in AP Physics 2. So this video, made together by Brandon, Alan, and Mikey, is designed to help prepare you to do your best on the AP2 test. So in order to get the most out of this video, you're going to be expected to already have background knowledge in the kinetic theory of gases, heat, and fluid mechanics. Fluid mechanics less so, but it's important that you understand pressure exerted by a gas and what exactly pressure is. Now, the kinetic theory of gases is essential to understanding the Carnot Engine, so make sure that if you're not already familiarize yourself with the following equations. We've got Pivnert, or PV equals nRT, also known as the ideal gas law, as well as the combined gas law. P1 V1 over T1 equals P2 V2 over T2. So I'm not going to go too in-depth here, but essentially, these formulas are going to be used in almost every Carnot Engine type of question that you solve. Now, heat is another important one. Heat comes up earlier in Ms. Sherman's thermodynamics lessons, and heat is not to be mixed up with temperature, as you guys surely already know. Often designated by the variable Q, heat is essential in understanding the Carnot Engine. So, moving on. So, first and foremost, you have to understand that in a Carnot Engine, you're describing the internal energy of a closed system. Now, what this means exactly is, take for example, a piston. So right here, these are going to be the walls of our cylinder or box or whatever you want to call it. And this right here is going to be the piston itself. So say this is a sealed container, and then we have stuff going on here. So all in here, we're going to have gas. Gas is spread out. And the piston is going to be moving up and down in a cyclical process doing work. So that's where the engine part comes in. Now the internal energy describes the internal energy of this gas. To those of you who are familiar with the kinetic theory, internal energy equals the kinetic energy of a gas plus its chemical potential energy, which we'll just call chemical energy for right now. We are just going to be worrying about the kinetic energy part of that, because this is a physics class after all. So, the important part of the kinetic energy is how it changes in this system. So we're going to call that the change in internal energy, and it can change in one of two ways. Either by adding heat, which is Q right here, or by doing work on the system, or the system doing work on its environment. So that's why you see this plus minus right here. So what this means exactly in terms of our physical example here, where remember this is one sealed system, the gases cannot escape through here or there, is that in each step of this cylinder's process, this engine's process, it's either gaining or losing heat, doing or receiving work. Now, it's important to understand exactly how work is done. In this example, work is done by changing the volume of a gas through the formula pressure times change of volume, which equals work. Now, how does that equal work exactly? Well, this is where the fluid mechanics comes in. Pressure, we know, equals force over area. And volume essentially equals change in a height times an area. So, if we cancel these out, that's force times change in height. So in this case, we're left with force times distance, because the height is a distance, which brings us back to work being done. Now, understanding how to calculate these is essential for solving a Carnot Engine problem, and Alan is going to be explaining further exactly how they're used, especially visually. Now, heat is a bit trickier. Oftentimes when you're solving Carnot Engine questions, you can't solve for the heat directly. You can solve for the change in temperature from one point of the process to another, or for the work that was done. The heat, you're often solving by taking the difference of the internal energy and the work. Now, this formula isn't exactly as clear as this one, but the change in internal energy is equal to 3/2 N R times change in T, T being temperature. Now, if you're familiar with your kinetic theory of gases, nRT describes the kinetic energy, and by taking the delta of the temperature, additionally with the 3 seconds, you're describing the entire internal energy of the system. Now, this is a formula that's best to simply be remembered because it's used so frequently. Now let's talk just a little bit more about this picture of a piston in a cylinder. So remember that this plus or minus means that work can either be adding or subtracting to the internal energy. Now, rather than figuring out which sign to use by plugging into this formula, it's best just to think about what exactly is happening. If the piston is being pushed down, as this arrow indicates, the gas is being compressed. When it's compressed, because of our ideal gas law, we see that pressure increases and therefore temperature must also increase, so the internal energy increases. So in the future, just always think that a gas compressed is adding energy and a gas expanding is losing energy. So, therefore, the reciprocal of that is the piston expanding, or the gas expanding, which means that the system is losing energy. So just think about it in those two simple ways. Now, heat is, as I said before, a bit more indirect. If the temperature of the gas increases, but there's no work being done, then it must be attributed to heat. And that's where we see this formula come into play once again by combining what we've talked about previously. Now, for the most part, the two formulas we talked about previously, along with the kinetic theory formulas, are going to get you through any Carnot Engine problem. So just to go over that again quickly, the change in internal energy equals 3/2 nR delta T. Remember, little n here are moles, and R is simply our gas constant, which in most cases is going to be 0.8321. But I'm sure you guys already knew that. So, work equals pressure, change, and volume. Now, there is one funky case, and I mean it, I really do, where work isn't equal to this. It is, actually. You just can't use this formula anymore. That's because the pressure isn't going to be constant. So, when the pressure isn't constant, but you need to calculate the work, you're going to use the formula work equals negative nRT times the natural log of the final volume over the initial volume. Now, because this formula is essentially derived using calculus, you're not going to have to know it for the AP test. But it is a handy tool, and it does come up in Ms. Drummond's class more often than not. So, when solving for what's called an isothermal process, which Alan's going to talk more about, and the pressure isn't constant, you're going to be using this formula to solve the work being done. Unfortunately, you're just going to have to memorize it. But you're going to be good knowing it for just a couple of weeks. So to get a more hands-on or visual example of how a thermodynamic closed system operates, we're going to be taking a look at this neat pneumatic claw that we managed to borrow from Mr. Yip's class. So what's essentially happening here is that, just as a quick demonstration, there is a limited amount of gas in these two syringes and the tube in between them, and when work is done on them, the result is seen in the claw. Now, to relate this more to what we talked about with the Carnot engine, as you can see, there is a fixed amount of volume to begin with when it's at rest, and the pressure will remain at 1 atmosphere. So that is essentially our formula: pressure times change in volume. And so when I here change the volume of the two syringes and I do work on the gas, in order for the pressure to remain constant, the work is then transferred into opening the claw. This claw has mass and is accelerating through a certain distance, which is therefore also work or energy. This also shows energy remaining constant, essentially transferring from the work I'm doing on the gas in here, and then the gas doing that same amount of work to open this claw.
Alright, so what is a PV diagram? A PV diagram is generally just used to show the relationship between pressure and volume, if you couldn't tell from P and V. And basically, we use these to find the work done by a heat process, and then we want to also find out the changes in both heat and, oftentimes, very importantly, internal energy. Now, a big deal with PV diagrams is you have multiple types of processes. So if you're going to fully understand these and know how to deal with them when they come up on a test, you're going to need to know those 4 types. So here I have 4 small graphs, and we're going to be running through all the types. We're going to be talking about adiabatic processes, isothermal, isobaric, and isovolumetric, also known as isochoric. And probably looking at these, you can sort of get an idea of what they might be all about. The really strange one is adiabatic. So with adiabatic processes, Q is constant, and we know Q is heat. And then if we go to isothermal, we know that T is constant, and we all know that T is the temperature. Now the next 2 are fairly obvious now. No, isovolumetric, V is constant. And then isobaric, we have pressure being constant. So these all have pretty different looks to them. The 2 that are very similar in how they look, though, and can be confusing, are the adiabatic process and your isothermal process. So adiabatic sort of goes like that. So it's a lower curve, whereas isothermal begins to even out much more quickly, meaning that you're going to have a pressure closer, and it takes less work for an adiabatic process to move from one to another. Isobaric, we know pressure is constant, so it will be a straight line. I know that isn't super straight, but for all intensive purposes that is straight. And then isovolumetric, you have straight line. So by looking at these basic types of graphs, we can sort of start to piece together what exactly these PV diagrams are doing. We know that P is your y-axis, so pressure is your y, and then V will be your x. And right now, these graphs might not seem all that important to what we need to understand, but as you can see, I've added these lines on the side, and the area underneath the curve will be very important coming up shortly. But first, I want to show you guys, if you have a point on one of these, and you have all the information, and you know what type of process it is, it's generally very easy for you to switch and find a second point using that process, using these formulas. They're a little bit hard to memorize, but once you get a grasp on them, you generally do not forget them, and they prove to be very useful. So for your adiabatic, we know heat is constant. So you get P1 V1 over T1 as your original point will be equal to P2 V2 over T2. So that, as you can see, is sort of like P1 V1 equals P2 V2, which is generally what everybody goes in understanding. And that exactly is for our next one, isothermal. Since temperature is constant, we know P1 V1 equals P2 V2. Isovolumetric is another pretty simple one. Be P1 over T1 equals P2 over T2. And then isobaric, continuing off this theme that we have, will be V1 equals, obviously V1 is over T1, V2 over T2. And we are doing this based off of the all-important formula. Let me use a different color just to highlight how important it is. PV equals nRT. Obviously, we don't have much of this involved right now, and I just went off the page. But as we go into these next formulas, we'll be able to see a little bit of those getting involved, because now we're going to be calculating the work done by a process according to the type of process. So let's calculate the work. So for your adiabatic processes, we will set work equal to negative 3/2 nR change in T. And we are able to simplify this because we have nRT is equal to negative 3/2 P change in V. And let me show you, just to make sure you understand what was happening there. This section right here, as we know, PV equals nRT, or in this case, nR change in T is equal to P change in V. We know this thanks to the formulas that Brandon gave us earlier on in the video. Isothermal is sort of similar, but at the same time, some might consider it a little bit more complex. We have W, work, equals negative nR change, just kidding, not change, nRT. Then we take the natural log of volume final over your initial volume. And that gives us the work done by the isothermal process. Isovolumetric is, some might consider it the easiest one, but let's be honest, isobaric is the easiest. Isovolumetric will always be 0. Isobaric now, pretty simple formula. Negative P change in V. Both of these obviously give you work. So now that we have that, let's just do a couple practice problems. Our first problem will be pretty simple to warm you up into it. Which process is depicted in these PV diagrams below? So, if we look at this, volume is constant. Pressure changes from these 2 points. So we know when volume is constant, it is isovolumetric. And if we wanted to go a step further, we could say the work done in this particular process is 0. This next one, we see this curve, and we know from what we saw earlier in the video that this sort of shape could either be isothermal or isovolumetric. I mean, so both the pressure and the volume are changing on this one. So we know it's not isobaric or isovolumetric, so it must be either adiabatic or isothermal. But right here we see T is constant, and we know isothermal is when T is constant. You know, isothermal. And say if we wanted to calculate the work, it'd be the area under the curve here. But since we don't know the actual equation for this curve, we cannot use calculus, so we will just write down what the formula is, which is negative n RT, then the natural log of the volume at the end over your initial volume. So now that we have that relatively simple problem out of the way, we'll go for another one before we get into a hard one. Now, the process depicted in the PV diagram below is isothermal. What is represented by the area under the curve? This is one of Ms. German's problems. It'll be one of the first ones that you take. And if you do not understand this, then you will not understand the rest of the problems. So, let's go from the bottom up. Is it heat converted? No. Change in internal energy. We do use PV diagrams to help calculate that, but this is not the area under the curve. Temperature of the process. No, this is not how we would do that. We would have to use one of our formulas using a point on this within the process to figure that out. Instead, we know it is work. So, circle that. We know that we're right on that one. And now, we'll go into one of the harder ones. Okay, so it says here, suppose a system of monatomic ideal gas at 2 to the times 10 to the 5th pascals and an internal temperature of 293 Kelvin slowly expands at a constant pressure from a volume of 1 liter to 2.5 liters. And they also helpfully give us this 1 liter is 1 times 10 to the negative third. So we need to find the internal energy. So if we want to find internal energy for, this says constant pressure, so isobaric internal energy is 3/2 nR change in T. So let's take a look. Can we do that right now? We have the pressure and we have the temperature. So we have one temperature, but it doesn't look like we actually have everything that we need. Obviously we have R, that is a constant 8.31. So I'd say our first order of business is to get N, the amount of moles of gas that we have. And the way we're going to get that, we know PV equals nRT. We want to solve for N. So P1 V1 over R T1 equals N. So P1, 2 times 10 to the 5th, T1, 293 Kelvin, V1 will be 1 times 10 to the negative 3rd. Since we're a little bit stressed for time right now, I'm going to go ahead and tell you that N is 8.21 times 10 to the negative 2 moles. So now that we have N, to solve this we need to find our second temperature. We know it's constant pressure, so we're going to set these two equal to each other. We know P1 V1 over T1 equals P2 V2 over T2. And since these pressures are the same, let me grab a different color, we are able to cancel them, leaving us with V1 over T1 equals V2 over T2. And as you can tell, we have 1 liter to 2.5. That gives us both of our volumes, and then over T1, which we have right here. So this will give us our temperature in Kelvin, which obviously, after you do the work, will give us 733 degrees Kelvin. Now that we have that, we are able to calculate by plugging in these values that we have. We have our moles right here, which will go right here. And then we have our temperature right here. So 733 minus 293. And there's there. And then we plug that in right here. R, as I said before, we'll circle that with this, 8.31 will go in there. And to make this long story short, we will end up with 450.3 joules as our change in internal energy. And I know it may have been a couple minutes, but this may seem daunting at first. Ultimately, we do know how to do this. Work is very simple for an isobaric process. Work is P, change in V, and lucky for us, we have change in V right there, and our pressure right there. So let's go ahead and make sure you see exactly what's going on. P will circle with this. Right there we have our pascals, and then move on to change in V will be 1 liter to 2.5. Obviously, we will convert those to meters cubed, but to save time, we will conclude there, and we now know that work is 3 times 10 to the second joules.
So what is efficiency? Well, efficiency is how well a engine converts heat or thermal energy into mechanical energy to do work. And the formula we're going to be using is E equals temperature hot minus temperature cold all over temperature hot. Now, what is a Carnot engine? Well, a Carnot engine is an ideal engine that goes through a reversible cycle, and it's the most efficient cycle there is. However, the Carnot engine is an ideal engine, and no engine can actually reach this efficiency, because the Carnot engine proves that it is impossible for the engine to convert all the heat energy into mechanical energy without sending some out to the environment, which then proves the second law of thermodynamics. So what is a Carnot engine? A Carnot engine is a theoretical thermodynamic cycle proposed by Nicholas Carnot in 1824, and it was expanded upon by others in the 1830s and 1840s, and it provides an upper limit on the efficiency that any classical thermodynamic engine can achieve during the conversion of heat into work, or conversely, the efficiency of a refrigeration system in creating a temperature difference. by the application of work to the system. It is not an actual thermodynamic cycle, but is a theoretical construct. Every single thermodynamic system exists in a particular state when a system is taken through a series of different states and finally returned to its initial state. A thermodynamic cycle is said to have occurred. In the process of going through this cycle, the system may perform work on its surroundings, thereby acting as a heat engine. A system undergoing a Carnot cycle is called a Carnot heat engine, although such a perfect engine is only a theoretical construct and cannot be built in practice. Essentially, there are two systems at temperature T hot and T cold, which are so large that their temperatures are practically unaffected by a single cycle. As such, they are called heat reservoirs since the cycle is reversible. There is no generation of entropy during the cycle, and entropy is conserved. During the cycle, an arbitrary amount of entropy is extracted from the hot reservoir and deposited in the cold reservoir. Since there is no volume change in either reservoir, they do no work, and during the cycle, an amount of energy is extracted from the hot reservoir and a smaller amount of energy is deposited in the cold reservoir. The difference in the two energies is equal to the work done by the engine. So a Carnot engine, its first point would be here, and it would go through an isothermal process down to here, and then an adiabatic process to here. But then to get back to where it originally was, so it's reversible, is it goes through another isothermal process to reverse what it did up here, and then a second adiabatic process to get back to its original point. Now we're going to head on over to a quick practice problem with the Carnot engine. So we're given a Carnot engine operating between reservoirs at 227 degrees Celsius and 27 degrees Celsius would have what approximate efficiency? So we're going to use the equation E equals temperature hot minus temperature cold all over temperature hot. And so we know that temperature hot is 227 degrees Celsius and that temperature cold is 27 degrees. So what we're going to do is 227 minus 27 all over 227 again. And that's going to give us about 0.88. So we know our answer is C.